The next time this parachute pops open, the lives of astronauts may be hanging in the balance. We're in the desert near Yuma to see if it is ready for a mission to the moon and back. And we're going underground into these caves to help you understand how researchers go billions of years back in time as they try to unlock the secrets of Earth's atmosphere. Hello, I'm Professor Vanessa Ruiz, and you're watching Catalyst. This YouTube edition of Catalyst is brought to you by Arizona PBS and Arizona State University. Life has problems. Science turns them into questions that can lead to solutions and even innovations. This is Catalyst, shaping the future through science research at Arizona State University. Picture yourself going about 15 to 20 miles an hour and then slamming to a complete sudden stop. That's the challenge for NASA engineers who've got to make sure that in that last mile coming back to Earth, astronauts can survive the landing. Astronaut Randy Bresnik knows what it feels like to fall from space back to Earth.
You go through the dangers of the entry with the heat shield and decelerating from low orbital velocities. There's that one moment where, okay, we should have chutes. Poof, the chutes come out, you feel the tug, capsule moves around a little bit, and then you get that deceleration feeling. That's when you can finally relax, going, hey, I'm going to be coming safely home.
Bresnik is an expert on NASA spaceflight and parachute systems. He is a veteran of 2 space missions. Today, he's at the Yuma Proving Grounds, a bombing range in Arizona. He's here to see the final drop test of the Orion parachute. The chutes are a vital part of NASA's new Orion spacecraft, the next manned spacecraft to go to the moon and back.
The dawn of Orion and a new era of American space exploration.
We are building the largest rocket ever built by humans and putting a capsule that's going to go out beyond low Earth orbit for the first time with humans since 1972.
Orion has 3 main parts: the service module, which rockets the capsule into space, the crew capsule where the astronauts sit, and the launch support system, which breaks away once the rocket reaches space. The Orion program is different from recent NASA deep space flights because it includes humans, not just robots and rovers, real humans with lives, families, and a lot to lose.
These parachutes on every mission will be responsible for returning the crew safely to work. And this is the final qualification test.
We fully appreciate and we understand that everybody's that's going to ride on this vehicle, their lives are dependent upon this system. There are quite a few things that could go wrong today.
The parachute design is a decade in the making.
This will actually be over the 40th parachute drop test they've done here. Throughout all these drop tests, our team has learned a lot, and they've rolled these lessons into the design and manufacturing and installation of our parachutes.
The capsule flies through space at an incredible 20,000 miles per hour. As it falls to Earth, the atmosphere creates friction and drops the capsule's speed to 400 miles per hour. Like a driver tapping on her brakes, the Orion parachute system has multiple steps to slow its speed. 4 groups of parachutes now deploy in rapid order. The first group of 3 small chutes removes the capsule's top cover. The second group are 2 large parachutes. They're called drogues. These stabilize the capsule and slow it to 150 miles per hour. Next, 3 pilot chutes deploy and lift the last set of main chutes up and out of the capsule. This last set of 3 parachutes drop the speed from 130 miles per hour to a safe landing speed of just 15 miles per hour.
One of our 3 main parachutes could cover 4 or 5 houses.
We're landing today in the desert. Orion's designed to land in the ocean. We need all of those parachutes to work appropriately to get us into a test condition.
Parachutes have to work at the end of a mission or, in rare instances, at the very beginning of it if something goes wrong right after launch. Like in October 2018, when the Soyuz capsule aborted its launch minutes after liftoff because of a booster rocket failure. If that happens to Orion, the launch system will reorient the capsule and deploy the 4 sets of parachutes. Today's test will reveal how the parachutes work after both a completed mission and in case of an aborted one. Since today's test is only a simulated spaceflight, the capsule and parachutes are not falling from space. They will drop out of a plane that is flying 6 miles above the desert.
So now we're going to ride these drones down to as low as we possibly can. 3 pilots, 3 mains. And if you listen closely, you can hear those mains inflating, and there we go to the full open. And there we go, we've got touchdown.
After the capsule and pallet land, NASA engineers dash to see if the test was successful and to answer the question on everyone's mind. If astronauts had been inside the spacecraft, would they have survived this landing?
What the parachute team does is they go find every little piece that comes off the spacecraft throughout the parachute deployment sequence.
There's foam panels on the bottom of this capsule. They're sacrificial, so they will have fallen off. You'll see quite a bit of debris when you get there, and all that's completely normal.
And they pick everything up and they look at it to see if there's any unusual wear and tear, anything that could give them an indication that something didn't work right.
Folding up the parachutes takes a lot of teamwork and coordination. Everything will be examined later for flaws.
If there were crew on board, if this were the real Orion with our astronauts coming back from the moon, and we saw what we just saw today, it would have been a nice smooth landing and the astronauts would have been very happy.
By completing this final drop test, the Orion parachute system is now ready for space flights with real human astronauts.
This one critical system that is supremely important to the crew members arriving safely back on Earth has been completed and is ready for flight is a huge milestone.
All of those mountains behind me were once erupting volcanoes, spewing lava as they rose higher and higher. But I want to direct you to another mountain right here. That's Mount Eldon. Now, it's strangely similar to a volcano that's recently been found on an asteroid. Space scientists are finding volcanoes on other planets and even smaller objects. And because we're building up a pretty good understanding of volcanoes here on Earth, any volcano we find in space can be a treasure trove of information about another world.
We want to understand how the solar system formed. We want to understand why it is different. And one of the ways we can do that is by studying these very small bodies that we think are primitive remnants left over from the formation of the solar system.
2 examples are the giant asteroid Vesta and dwarf planet Ceres. These 2 objects have stood the test of time in the asteroid belt between Mars and Jupiter. NASA's Dawn spacecraft launched in 2007, tasked with studying both asteroids during a historic trip inside our solar system. That trip came to an end in late 2018 when the craft ran out of fuel and lost its ability to communicate with Earth.
When you work on a mission this long, it feels like a part of you.
ASU professor David Williams worked on mapping Vesta and Ceres as a member of the mission science team. He's watching NASA's final mission update. During its 11 years on the job, the Dawn spacecraft helped scientists like Williams learn a great deal.
When the spacecraft arrived at Vesta in July of 2011, I was hoping to map the volcanic deposits we saw on the surface. But in fact, the surface of Vesta is so completely pulverized by impacts that all of the volcanic features are missing. The reason why it's not round in shape is because there were 2 large impacts that struck the south polar region of it, and those impacts produced craters on the order of 400 to 500 kilometers in diameter. And those impacts were so powerful, they're what actually excavated all of the material that we now recognize as this whole family of meteorites that fall on Earth. When Dawn got to the dwarf planet Ceres, we saw these unusual bright spots in one impact crater named Akator. It's a 92-kilometer diameter crater, and right in the very center are these very, very bright materials that are very different from the rest of the surface. And when we looked at them up close, it turns out that they're made out of salts and carbonates, and they were placed in a form suggestive of volcanism. So seeing these exotic volcanic-like deposits yet made out of a totally different type of material than the way volcanism occurs on Earth was absolutely astounding. And we also found it in the form of a mountain. Ceres only has one mountain 4 kilometers high, but it looks very much like what we on Earth would call a silicic dome, a very viscous magma that will form a mountain, much like Mount Eldon in Flagstaff, yet it's formed out of a totally different type of composition of material. So those were the most astounding things, I think, that we've discovered from the Dawn mission on these two very unique bodies in the main asteroid belt.
The Dawn spacecraft's incredible journey was only possible because of a technology called ion propulsion. It may sound like something out of science fiction, but imagine 2 magnets. When you try to put the 2 positive sides next to each other, they push each other back. This is the basis for ion propulsion. Here's how it works. Inside the spacecraft's discharge chamber are magnetic rings. They create a magnetic field. Add a propellant injector and a discharge cathode, a screen electrode, and an accelerator electrode. Above it all, what's called a neutralizer. You need an electron, a neutral atom, and a positive ion. The neutral atom is released with an electron. They collide, and ionization occurs. The positive ion accelerates through the electrodes. An electron is released from the neutralizer. The process repeats, and what you get is thrust that moves the spacecraft. In the vacuum of space, these atoms provide enough thrust to get a small spacecraft, like Dawn, through our solar system and into orbit of an asteroid like Vesta.
This is the first time in robotic exploration of the solar system where we actually sent a spacecraft from Earth using ion propulsion. It orbited one body, Vesta, and spent time studying it there. Then it departed Vesta with that ion propulsion, went to another body in the solar system and orbited that. And using a very inexpensive ion propulsion to do that opens up this technology for many, many future missions.
Depleted of fuel and no longer functional, Dawn will remain in silent orbit of Ceres indefinitely. But its mission has paved the way for future exploration of the asteroid belt and other objects in our solar system.
The way we design and build planetary missions and the way we conduct solar system exploration, we do it in a very phased approach, and we do in the form of flybys, then orbiters, then landers, then rovers, robotic sample return, and finally human missions. And so with this first reconnaissance of Vesta and Ceres with the Dawn orbiter, we now know what's there. We now know what the geology is, what the history is, and now we can better inform the concept and ask the question, what should be the next mission? What should we do? For many of us planetary scientists, we recognize that the ultimate goal is to transform humanity into a multi-planet species. We want to develop a spacefaring civilization. And the first step is to do that close to home with the moon and the near-Earth asteroids, identify what kind of resources they might have to build bases on the moon, to build the infrastructure to eventually send humans out to Mars and elsewhere in the solar system. These are the resources which we are going to eventually want to use to help humanity become a permanent spacefaring civilization.
Don't worry, I'm not going to smoke this. When a cigar is lit, you get 2 things: the glowing red of the burning tobacco and the smoke coming off that combustion. Now, this may seem like an odd way to get into talking about space science, but when we look up into space at stars and try to learn more about them, this is kind of what it comes down to. Getting images of light and of smoke, or in this case, of stars and gases. Philip Maskoff and his research team have been building a telescope to study the smoke-like dust and gases in the depths of space.
The smoke, which takes up a lot bigger volume and area of space, at longer wavelengths, like in the infrared, if you look at a fire, you actually see the smoke because it's warmer than the surroundings. So at the long wavelengths, what we are looking at is the smoke and the gas that are given off by the stars, and they're primarily given off by stars when they're forming.
One of the tasks is understanding star formation, and one of the big unknowns is what role magnetic fields play. And so by mapping the magnetic fields in these star-forming regions, we will better be able to understand, or at least build models which can create these field patterns.
The team hopes to use the images from the telescope to create electromagnetic maps of the observable sky.
We're bringing new information down to the Earth, basically, from the cosmos, and getting our hands on it so that we can begin to understand it.
Now, you can't capture these clouds of smoke and gas with a regular camera, so Mascroft and his team have been developing their own. But this hot new camera needs to be kept extremely cold.
These detectors require the low temperatures in order to operate. So we have a cryostat, which we test most of these devices in. A cryostat is a thermos, which has insulating walls, and we want to vacuum it out so that there is no physical contact and there's no heat transfer between the different layers.
We want to measure temperature changes, which are extremely small, and we need our detectors to be at a much lower temperature than what we're trying to measure.
The sound you're hearing is the cryostat working to cool down those detectors down to a temperature of minus 450 degrees Fahrenheit.
In the most emptiest parts of space, it would be 2.7 Kelvin. So this is actually much colder than that at 270 millikelvin.
In order to get the pictures they want, the scientists need to send their telescope into the highest reaches of the Earth's atmosphere. Their strategy for doing that may be somewhat surprising.
Normally, when you talk about launching something, you usually talk about launching a rocket or launching a satellite into space. When we tell people we're about to launch a telescope from Antarctica, they're always surprised to hear that we're launching it on a balloon.
Balloons are cheap. The cost comparison is sort of, it's on order on the scale of $1 million for a launch of a balloon compared to, on order of tens of millions or $100 million for a satellite.
And liftoff of Space Shuttle Atlantis.
And you can't launch a 6,000-pound telescope for $100 million. That's a big telescope. That's more a $1 billion scale. Your daughter, right, with her helium balloon, it's fun to play with, and it floats. But if you had one that was the size of a football stadium, then it could carry you pretty high. It can carry it to 125,000 feet, 3 or 4 times higher than an airplane flies. You're above 99.7% of the atmosphere. The sky is black at that point. You are almost in space.
They plan to take the telescope to Antarctica this December, and it will not be their first time.
NASA has had a long-duration balloon program in Antarctica for about 25 years because there's no people there, and people generally don't like knowing that there's a 6,000-pound telescope that's hanging from a giant helium balloon flying over their house.
Blast TNG went to Antarctica last winter as one of 3 teams with balloon launch plans. They've worked around the clock for weeks to test and retest various elements of the project.
Nothing has gone exactly according to plan, and so we've had to solve a lot of puzzles along the way.
Whether it's small balloons like these or one of the big ones that lift the telescope, you have the same challenges. Sunlight, wind, and even air temperature can all affect how high the balloon goes, how long it stays up, and whether it goes where you want it to go. So all of these factors come into play when deciding if a telescope balloon is even going to get on the launch pad.
In terms of fears on launch day, it's the unknown unknowns which are most frightening to us. There are some known risks, for example. Equipment can be damaged during the launch, especially the optics. You don't want your primary mirror to be damaged.
The biggest moment of anxiety on the launch is the balloons sometimes leak.
The Blast TNG scientists watched 2 other teams launch their projects, anxiously awaiting their own turn. Those 2 other projects were forced to come back down early due to leaky balloons.
And it looked like we only had 1 launch date remaining. So we ended up coming out to the launch pad. When you're on the launch pad, 90% of the time, you're going to be flying. So everyone was feeling obviously very excited, and Mark comes in. He's kind of shaking his head as he's walking, and he just says very matter-of-factly, "We're not flying. It's canceled." At the last minute, the winds picked up out of nowhere.
Minutes before takeoff, on the last potential launch day of the season, the team's launch was canceled.
90% of the battle is getting to the point with a team of people where you are actually able to be on the launch pad. And that in itself is a victory. That's its own reward. Of course, getting a whole massive payload of interesting science data is another type of reward, but on a personal level, it's the journey getting up to that point that is what really matters.
BLAST TNG will return to Antarctica later this year when NASA's next long-duration balloon season begins all over again. Here inside the caves of Kartchner Caverns, you can really see what a powerful force water can be. Now, water has been forming and changing the strange shapes in here for 200,000 years or more. Water and water vapor are so much a part of these caves that the air I am breathing right now stays near 99% humidity all the time. Water seeping, flowing, dripping through and around limestone. Limestone is made of the skeletons of tiny ancient sea creatures. But let's go back even further. Not tens of thousands, but billions of years. Earth had water and oceans, but before Earth could get its plants and sea creatures and the entire explosion of life on our planet, it needed oxygen in the atmosphere. So researchers are now asking two big questions. Where did all of that oxygen come from? And why does it seem that it all appeared so suddenly?
So my research interests are about trying to understand the evolution of the Earth as a habitable world. How did the planet get to be the way it is? What does it look like now? How does it work? And what's the future of the planet? I'm Orion. I'm a professor in the School of Earth and Space Exploration and in the School of Molecular Sciences at Arizona State University. And I also direct the Center for Education Through Exploration. But probably most of my group's research has focused and continues to focus on trying to understand what the Earth was like 2.5 billion years ago, about halfway through Earth history, when we went through a transition of the planet from a planet that had almost no oxygen in the atmosphere to a planet that was on its way to having 20% oxygen in the atmosphere as it does today.
Inside a place like Kartchner Caverns, you could learn a lot about the past by taking a sample of the rock, or even checking the minerals dissolved in the water that flows in the cave. But how do you sample something from several billion years ago?
We don't have samples of ancient air. We can actually get samples of ancient air from ice cores, but that only goes back at most, maybe 1 million years. And here we're talking about billions of years ago. So there's no way I can grab a sample of air. There's no rock where I can find a little bubble of air that's 2.5 billion years old. So we got to be indirect about it. And so what we do is we look at the chemical composition of sedimentary rocks. Rocks that are formed from sediments that were laid down in ancient oceans that have chemical compositions that reflect the chemistry of the water. And the chemistry of the water is related to the chemistry of the atmosphere for gases like oxygen that dissolve in water.
So you take an old rock, you kind of crush them up into this powder. I'm going to start to add different types of acid, which is going to dissolve all this powder. And then we're going to analyze the different elements that are in that solution.
And oxygen, when it's dissolved in water, causes chemical reactions that leave a fingerprint in those rocks. It's kind of amazing, right? We can look at the chemical composition of ancient rocks and say something about how much oxygen was in the atmosphere at different times in Earth history.
There are trails in the mud right here inside Kartchner Caverns. Those are the footprints of the two explorers who first discovered these caves. It kind of puts you back in that excitement of discovery, but it is also a reminder that whenever we discover something new, we do run the risk of changing it. In a way, workers in Ambar's lab face a similar problem.
So we make all these measurements here at ASU. We have a world-leading lab, and that lab includes what's called a clean lab, a trace metal clean lab. It's a lab that is all made of plastic. Everything, as much as possible, is made of plastic because what we're trying to measure in these ancient sedimentary rocks are the abundances of different metals. Metals whose chemistry in the environment is shaped by oxygen. And so the last thing we want is to have to worry about rust flakes floating around in the lab. And so we do all our chemical preparation there. We take these rocks, we dissolve them in acid, we do a process called chromatography to separate the elements out. And then we take that to the other part of the lab, which is the mass spectrometry lab.
This is our multi-collector mass spectrometer, and it allows us to understand the isotopic composition of our samples. So what happens is we put our samples in this auto sampler. It uses a straw to suck up the sample. It goes then into a plasma, and the plasma is really, really hot. And what that'll do is it'll ionize our sample, and it'll then go into Faraday collectors where we can measure the mass to charge ratio of our element of interest.
It turns out the tools designed to help answer these very big questions about how the Earth came to be the way it is can also be put to use to answer important questions about medicine and keeping our bodies healthy.
The same kind of chemical reactions we think about in ancient rocks also go on in your body. And just like we can infer things about ancient environments from measurements of these things in ancient sedimentary rocks, we can infer things about your body by making these measurements on fluids or tissues from people. So we have a whole line of research in my lab looking at calcium as a way of telling whether you are making bone or losing bone in your body. You're always doing both. The real question that the physician wants to know, especially if you have a bone-related disease, is the net effect of the bone formation and bone removal processes going on in your body. Are they in balance? Or are you net losing, or are you net gaining? So there aren't any good ways to do that. So our technique actually provides a way to directly measure that, which can be pretty powerful.
I'm Professor Vanessa Ruiz. Thank you for watching Catalyst, our show about science. And because science always has new questions to answer, we'll be back soon with more stories. Subscribe to this channel to see more episodes of Catalyst on YouTube.